perhaps you've heard about my personal favorite. We have a huge problem merging our different feature branches. We need to buy better merge tools. Again, there may be a social explanation for that. And I think the main reason that we keep making misattributions like this is because the organization that builds the system is invisible in the code. And this is unfortunate because there is a strong link between technical debt and the organization. And it's my firm belief that we cannot address technical debt unless we take a holistic view on the system. And that holistic view has to include a social view of your code. So, based upon what I've told you so far, what I did was that I took a step back and I put together a wish list on the ideal information I would like to have in order to prioritize technical debt. So I'm going to present that list to you, and let's see if you agree with me. The first thing I would like to know is, where's the code with the highest interest rate? The second thing I would like to know is, does our architecture support the way our system evolves? Are we working with or against the architecture? And the final point, and perhaps the most important one, are there any productivity bottlenecks in our code for inter-team coordination? You know those parts of the code where 5 different teams constantly need to coordinate their work. Now, I want you to think back to the code you're working on right now, the system you're involved with right now. Does any one of you think that this information could be potentially useful to help you make decisions around that code? Oh, I see plenty of hands. That's really, really good. Thanks a lot. Otherwise, this will be a really short presentation. So, the interesting thing here is with this information that none of that information is available in the code itself. It's invisible in the code. More precisely, we miss some critical information. And we need that information in order to make informed decisions around technical debt. And I've told you that most prominently, we miss a time dimension and we miss social information. So, how can we get that? Where's our crystal ball? It turns out you all already have one. We're just not used to think about it that way. I'm talking about the version control system. Our version control system is an informational goldmine. Most of the time, we use version control as a way to collaborate in code and sometimes as a complicated backup system. But when you look closer at it, there's a lot of valuable information there. First of all, version control data, and you see a simple example from Git here, if you can read it with that resolution, it's that we get a time dimension, because Git knows exactly at what point in time we committed our changes, right? And we can use that to calculate a lot of interesting statistics and frequencies. And the second piece of information that we get is that we get a social view of our code. We get social information because version control data knows exactly which programmer that did what change. So let's embrace version control data and let's see how it helps us identify the code with the highest interest rate. And the technique I use to identify that code is an analysis called hotspots. Here's how it works. What you see here is a hotspot analysis of a well-known Java code base. It's an old, mature Java code base that some of you probably know pretty well. This is Tomcat. And the way this works is that you see those large blue circles here, the ones that blink on screen. Those circles represent a folder in your code base. And you see other blue circles inside them. Those are subfolders. So this is a hierarchical visualization that follows the folder structure of your code. It's also an interactive visualization, so we can zoom in on the areas of interest. And when we do that, you will see that each file is represented as a circle. And you will see that they have different size. That's because size is used to represent code complexity. How do we measure code complexity? Well, we have a bunch of different metrics in our industry, things like cyclomatic complexity or Halstead's volume metrics. And we can basically use any metric we want because what they all have in common is that they're equally bad. So I tend to recommend the simplest thing that could possibly work, which is actually the number of lines of code. It turns out that's actually a pretty decent approximation of code complexity. And besides, this is not important information, because I told you just a few minutes ago that just because some code is complex doesn't mean it's a problem. It's not a problem unless we have to work with it. And that's information we can pull out of our version control data. So we pull out the change frequency of each file and use that as a proxy for interest rate. And the interesting thing is when we combine these two dimensions, because now we're able to predict complicated code that we also have to work with often. And those are our hotspots. So let's return to Tomcat. We see a number of hotspots in Tomcat. And those hotspots, that's the piece of code that requires the most effort from you. This is the code where it's vital, that it's clean, easy to evolve, easy to maintain, because that's the code where you spend most of your time. However, I've found that in practice, more often than not, the opposite is true. And that tends to make hotspots really, really good refactoring candidates. And there's a fascinating reason why hotspots work so well to prioritize technical debt. And the reason is that I have found that while all code is equal, some code is more equal than others. Let me show you what I mean with this. So please have a look at the following graphs. Each one of them shows exactly the same thing. On the x-axis, you have each file in the system, and they're sorted according to the change frequencies. That is, how often do you make a commit to that particular file? And the number of commits is what you see on the y-axis. Now, the example data here shows data from 3 radically different code bases, developed by different organizations, targeting different domains of different size, different lifetime, different technologies. Everything's different. And yet, do you see any similarities in the patterns? That's right. They all show exactly the same pattern. They show a power law distribution. And this is something I found in every single code base that I ever analyzed. This seems to be the way software evolves. And this is important because it gives us a tool to prioritize. Because what it means to you is that you tend to spend most of your time in a relatively small part of the code. Most of your code is here in the long tail, which means it's code that's rarely, if ever, touched. So this is the concept that hotspots build upon, and that's what makes them good to prioritize and identify code with the highest interest rate. But sometimes hotspots aren't enough. In some cases, we need much more detailed information in order to act upon it. And I would like to show you an example of that by turning to a different case study. I would like us to investigate the .NET Core runtime from Microsoft. So what you see here on screen is a hotspot analysis I did a couple of months ago of the .NET Core runtime. And at that point in time, most of the hotspots were here in the JIT package. But you also see an interesting satellite there, a file called gc.cpp. Now, gc.cpp is the .NET garbage collector. And I have to tell you that gc.cpp, it looks quite innocent on that visualization, doesn't it? But that's just because the scale of .NET Core. .NET Core is huge. So what you see here on screen is approximately 4 million lines of code. And gc.cpp is a big file. How big? I don't know, so let's look it up on GitHub, shall we? Turns out gc.cpp is too big to visualize on GitHub, so we need to look at the raw file. And when we do that, we find out that gc.cpp consists of 37,000 lines of C++. 37,000 lines of C++. Let me tell you, I used to be a C++ developer. I did C++ for 10 years. I know, that's 10 years I'll never get back. But what that means to me is that I cannot think of a more scary thing than 37,000 lines of C++ in a single file, right? And besides, how helpful would it be to learn that gc.cpp is a hotspot? So how do you react on that information? if I come to you and say, hey, I found most of your maintenance problems. You just rewrite this file with 37,000 lines of code and most of your problems will go away. How would you react on that information? The answer is you don't. You need much more detailed information. So what I suggest is this. Remember that I told you that all code isn't equal, right? We spend more time in particular files compared to others. And I found that the same thing holds true on a function level. So what I suggest is that when we have those big files, we take them, we parse the source code, and then we try to correlate different commits to individual functions. And then we run a hotspot calculation on a function level, right? So what I'm going to show you now is a hotspot analysis of the functions in gc.cpp. Here we go. It turns out our number one hotspot on a function level is a function called grow brick card tables. It's a pretty big function consisting of 332 lines of code. That's a lot for a single function, isn't it? But it's much less than 37,000 lines of code, which is the size of a total file. And it's definitely less than 4 million lines of code, which was the size of the total system. And more importantly, we are now at the level where we can act upon this information and do a focused refactoring based on data from how we actually worked with the code so far. We're going to return to our hotspots in a few minutes. But before that, I'd like to see how we can get to a file with 37,000 lines of code. You see, I just cannot let that go. So what you have here is one of the best books I know on how organizations fail. This book is called The Challenger Launch Decision, and it's written by Diane Vaughan. And in that book, Diane uses the Challenger accident as a foundation for her theory of normalization of deviance. So just to recap, what happened with the Challenger was this. See the picture here? That's from the final launch of the Challenger, the space shuttle. And you see that big object here in the front? That's a solid rocket booster. And you see that puff of gray smoke at the joint here? That's not a good thing. It's not supposed to be there. So what happened here was that joint in this solid rocket booster, it leaked and hot gases were able to escape and compromise the whole structure of the spaceship. And the story behind that is that those solid rocket boosters, those are huge rockets, right? And they're delivered in different segments that are then assembled. And it turned out that the early testing back in the 70s revealed that the actual performance of those joints deviated from the predicted performance. Now, what they did was they put together a committee, and that committee decided to pass off those deviations as an acceptable risk. Years later, the first in-flight tests of the space shuttle revealed that, again, the performance of those solid rocket booster joints deviated from the predicted performance. And again, it was passed off as an acceptable risk. And finally, on the very eve of the launch, there were some concerns about the solid rocket booster joints due to the cold temperatures in Florida at that time. And again, it was discussed and passed off as an acceptable risk. And the consequence was a terrible loss of human lives. So what Diane Vaughan tells us about the normalization of deviance is that each time we accept a deviation, those deviations will become our new normal. We get a new point of reference. And I found this interesting because the normalization of deviance is not about spaceships, it's about people. And we have the normalization of deviance in software too. So let's say, for example, that you inherit a file with 5,000 lines of code. If you work with that file long enough, those 5,000 lines are going to become your new normal. And besides, what difference does a few extra 100 lines of code do? So soon you have 6,000 lines of code, then you have 7,000 lines of code, and so on. And we need a way to detect that and to fight and stop the normalization of deviance. So I'd like to show you a technique that I found works really well in practice. This is a technique called complexity trends. So what you do here is basically you take each hotspot and then you pull out each historic revision of that code from your repository and plot the complexity over time like this. And you see two lines here on screen. The blue line is the accumulation of lines of code, And we see that this file keeps growing and accumulating more and more code, which may be a problem in itself. But the main concern here is that the red line, which shows one of the other complexity metrics, we see that it basically increases at a much more rapid rate than the lines of code. And using this data, we can basically read the system, the history of that hotspot. So we see here that last year we managed to do some kind of refactoring, so we decreased the complexity, but we probably failed to address the root cause because soon the complexity crept back in, and then there was a huge, steep increase in complexity here. The normalization of deviance is one of the main reasons that whistleblowers are so important to an organization. And I have found that complexity trends make great whistleblowers in code. So let's sum this up. Hotspots help us identify the code with the highest interest rate. And the reason hotspots work is because all code isn't equal. And we have seen that we can use complexity trends to supervise the growth of our hotspots. Now I want us to climb up the abstraction ladder and see how we can apply the same ideas to architectures. And as you know, you cannot really talk about software architecture without mentioning art. So last time I was in London, I went to Tate Modern, and I visited an exhibition by the artist Gustav Metzger. And you see an example here on his liquid crystal light projections. And those are quite fascinating, because if you stand and look at that artwork, it changes slowly before your eyes. So that artwork looks different today than it did yesterday. And the interesting thing is the way it changes. Because the way it changes is that it necessitates the destruction of an existing form for the creation of a new form. And this is exactly how software is supposed to evolve. It's also one reason why I'm so fond of hotspots, because hotspots make it clear that a code base is never done. Successful code evolves, and that's a good thing. However, the reason I say it's auto-destructive is because changes and new features tend to become increasingly more difficult to implement over time. And some systems just seem to reach a tipping point, and beyond that point, they become virtually impossible to maintain. So what I suggest is this, that just as we can calculate the complexity trend of an individual file, let's do that for every single file in our code base. Let's accumulate that information so that we can get the system complexity trend. And this trend may help us identify when and possibly predict if we reach that tipping point. And that tipping point is a sign that we need to take a step back and start to actively invest in real improvements. Now, where would those improvements be? Again, our hotspots may provide us with some guidance, but I would claim that in a large system, we need the information on a higher level. So what I suggest is that instead of focusing on individual files here, what we do is we group different files into logical architectural components. And then we aggregate all the contributions to those files and calculate hotspots on that aggregated level. And you can use any combination here that you want. You can aggregate based on folders. The important thing is that your groups should carry some architectural significance in your context. And when we do that, we can start to reason about how our systems evolve on our architectural level. And I would like to show you an example on that from a service-oriented architecture. And this is the kind of information that will help you answer one of the big questions we have around microservices. I promise you, many flame wars have been fought over this question. Friendships have been ended. And the question is, how big is microservice supposed to be? 100 lines of code? 1,000? 2,000? We all know it's a bit misdirected to reason about that in terms of lines of code. What we're after here is behavior. We want each service to implement a single business capability. So what I do in a service-oriented system here is that I aggregate all contributions for each service. And now we can calculate hotspots on a component level here, on a service level. And we see on that level, the number one hotspots, it's the recommendations service. And we can get more information because just as we can calculate complexity trends for individual files, we can aggregate it for a service and get a complexity trend for that service. And then we see that the recommendation service has quickly grown and seems to have stabilized at around 5,000 lines of code. Now, this helps us ask the right questions. And the right question here is, does this single service with 5,000 lines of code that changes at a high rate really implement a single business capability? Because I have found the main reason that code grows into hotspots is because they are low on cohesion. So I would use this data to inspect the recommendation service and see if we could possibly split that service into 2 or more independent services, which will benefit the overall cohesiveness of our system. But we can get even more data here. And I would like to introduce a concept called temporal coupling to you. Temporal coupling is interesting because it's something you cannot measure from code alone. Temporal coupling is only possible to measure from the evolution of your code. Here's how it works. Consider this simple system here. It consists of 3 different subsystems. And the first time we make a change to this code base, we modify the fuel injector and the diagnostics module together. The second time we make a change, we modify something else. The third time, we're back to modifying the fuel injector and the diagnostics module together again. Now, if this is a trend that continues, there has to be some kind of relationship between our fuel injector and the diagnostics module because they change together all the time. What relationship could that possibly be? Let's see how we can use this to focus on an architectural level and get insights into the architectural patterns we use. And I'm going to show you a number of examples from different architectures. And I'd like to start by talking about layers, because that's still one of the most popular architectural patterns. So most organizations that do layered architectures, they claim to do something like this. Some variation on the model view controller pattern. You may have model view presenter, model view view model, whatever, something like this. However, as we all know, that's never how it looks in practice. Because we all know we also need a services layer, right? And of course, we also need a repository layer. And the reason we need a repository layer is because, well, I actually don't know, so let's call it a best practice. And of course, we may have an object relational mapper and then maybe some SQL at the end. And it's quite likely that in practice we have even more layers here. Now, the reason I think that layers grew so popular is because they give us a sense of structure. They give us a separation of concerns. So what I would like to do to evaluate this pattern is to measure temporal coupling on a layer, the level of layers here. And when you do that, you will find that your change patterns in layered architectures look like this. In fact, I have found that somewhere between 30 to 70% of all the commits you do to a layered architecture ripples across layer boundaries. And this has several consequences. First of all, few changes are local. And this means that maybe layers gives us a separation of concerns, but perhaps it's the wrong concerns we are separating. And the reason I say this is because I found that this works pretty well for a small system with a small team. However, if you try to scale this pattern to a larger organization with more people, you tend to run into problems. Because since few changes are local, you tend to get unexpected feature interaction, conflicting changes, and all that kind of stuff. The code grows into a productivity bottleneck, which is something we're going to talk about soon. And I think this trade-off here with layers is one of the main reasons that microservices has gained so much popularity. And this is, as we all know, what microservices always look like in PowerPoint. In reality, we know that they are much more complex, right? We may have shared building blocks, service template, client APIs, cross-cutting concerns like monitoring, diagnostics, and so on. And what we want to do in a microservice architecture is to ensure that the services are able to evolve and be deployed independent. So one of the worst things we can do here is to start to couple different services to each other, because the moment we do that, we lose a lot of the benefits and promises of a microservice architecture. So if we have a fundamental principle like that, what I recommend is that we group all contributions, all files that belong to a single service into one logical component, and then we measure temporal coupling on that level. And now we use temporal coupling to watch out for patterns like this, where multiple services tend to change together. And once we identify that, we may use that as an early warning sign that helps us avoid what I call the microservices shotgun surgery pattern. And the microservices shotgun surgery pattern, it's basically the scenario, you know, when you want to tweak a single business capability and you end up modifying 5 different services. And the frequent reasons I've seen this happen in practice is that those different services, they may share code that itself isn't stable from an evolutionary point of view. Another reason I've seen it happen is that some services are just leaky abstractions, and they expose implementation details that others depend upon. And I've also seen this happen a bit more frequently when the same team is responsible for multiple services that are closely related. And by using temporal coupling as an early warning system, you can identify those patterns, which gives you time to react before it becomes a big issue. All right, what kind of tools do I use to do this kind of analysis? I have to tell you that this is a really young field, so the tooling options are quite limited. In fact, when I wrote my book, Your Code is a Crime Scene, a number of years ago, there were no tools available that could do the kind of analysis I wanted to do. So I put together my own tool suite, which I've open sourced. It's available on my GitHub, completely free. I still maintain it. And it may be a good starting point if you want to experiment with these techniques on your own code base. What I work on these days is a tool called CodeScene. And CodeScene is my attempt at automating all this stuff. So it's basically press a button and get the results. It's also available for free for an open source project at CodeScene.io. There's also some interesting tools in the academic field. One of my favorites is the evolution radar, which is particularly strong on temporal coupling. And then, if you would like to build your own tools, I recommend that you have a look at the Moose platform. The Moose platform is not only a great framework, it's also a perfect excuse to learn to program in Smalltalk. All right, let's sum this up. We have seen that hotspots also scale to an architectural level, which let us get insights into how our systems evolve. And we've also learned how we can use temporal coupling to evaluate our architectural patterns and how well our architecture fits the way we actually work with the code. Now, I would like us to spend the last minutes here by exploring the social side of our code. More important, I want us to try to identify productivity bottlenecks for inter-team coordination. And before I start here, I would like us to do a small exercise together. Could everyone please raise both of their hands like this? Cool, great, great. All of you, come on. Perfect. Now, keep your hands up if you develop software as part of a team. Few hands went down. Most of us develop code as part of a team. Thanks, you can take down your hands. You look amazing, by the way. And the reason we do that is because we need to organize in teams because we have to take on larger and larger problems. However, what I want us all to remember is that teamwork isn't free. It comes at a cost. And that cost is called process loss. And process loss is a concept from social psychology, and the social psychologists have borrowed it from the field of mechanics. And the idea is that just like a machine cannot operate at 100% efficiency due to things like friction and heat loss, neither can a team. So the way it works is this. We have a bunch of individual contributors, and together they have a potential productivity. However, that's never, ever what you get out of a team. The real productivity is much smaller, and part of that productivity is simply lost. And the way it's lost depends upon the task you do. But I would say in a field like software, most of that process loss is due to communication and coordination issues. And one common reason I've seen for process loss in software is something called the diffusion of responsibility. And before I move on, I have to warn you here, because now I'm going to talk about a really controversial topic. I'm going to go out on deep water here and do something completely crazy. Something you never do as a speaker at a conference. I'm going to talk about code ownership. Yeah, that's right. And just to make sure, what I mean when I say code ownership is, I don't mean ownership in the sense of, hey, this is my code, stay away. No. I mean ownership in the sense that someone feels a personal responsibility for the quality and the future of a piece of code. And that someone could be an individual or a small team in a large organization. With that sorted out, what's diffusion of responsibility? Diffusion of responsibility is again a principle from social psychology, and it's something you can witness if you're unfortunate enough to see an accident or an emergency. Because it turns out, the larger any group of bystanders in those situations, the less likely any individual will offer help. It's actually quite scary. And there are several reasons for that, but one of the main reasons is that in a large group, we no longer feel that sense of personal responsibility, and besides, we always assume that someone else will help. And it's exactly the same in software. And I'm pretty convinced that good code means that's code where someone has a personal responsibility. Good code is personal responsibility from everyone involved in it. And I don't think there's any way around it. So how can we measure things like team coordination and the diffusion of responsibility? It's easy. Remember, we're in version control wonderland. Our version control system knows exactly which programmer that did what change. So let's aggregate that information into teams as represented in our organization. Here's what it looks like. This is the same kind of visualization as we used for the hotspots, only now the color carries a different meaning. The color here represents the team coordination efforts. And the way I measure this is, I use an algorithm that is from a research paper that I reference here. And I want to point out that it's not only about how many different teams that need to coordinate in a piece of code, it's also how diffused their contributions are, as measured by version control data. And there are several reasons you want to measure this. It's not only about increasing productivity, there's also a quality aspect. Because it turns out there's pretty good empiric research that shows that the number of contributors to a piece of code is one of the best predictor of the number of quality issues you will have in that code. So it makes sense from a quality perspective too, to investigate and identify those areas where you have high inter-team coordination needs. And once you have found those areas, there's usually no easy fix. The things I've seen work in practice are two main themes. The first is that once you've identified code like this, you know, the more red, the more coordination needs, you need to investigate it from a technical point of view. Because again, code changes for a reason. And the reason a piece of code attracts many different teams is probably because it has many reasons to do so. It has too many responsibilities. So taking that code, identifying those responsibilities, and split it in smaller modules, smaller, more cohesive modules, helps you reduce the need for inter-team coordination, which not only improves your efficiency, but also has nice quality benefits. The second thing I've seen is that sometimes you need to introduce a new team into an organization in order to take on a shared responsibility. And this is something I tend to find quite often in areas like this, where you have automated integration tests. But we can do even more with this data. So the final thing I want to show you is how we can start to measure things that we normally only talk about. We can start to measure things like Conway's law. And you see an example here. It's the same visualization style, but now each color represents the contributions of different teams. So this is a package by feature architecture, and you see that from the perspective of Conway's law, this looks absolutely fantastic, right? So each team can work in their dedicated part of the system, and we have a minimum of inter-team coordination needs. This is absolutely amazing. However, I also have to make a small confession here. All data, all visualizations that you have seen so far are from real-world code bases, except this one. I had to make it up because I'm yet to find an organization that's well aligned with their code. So let's look at a more realistic case. This is a real code base, and this is an organization that decided to move to feature teams. So they basically took the organization and split it into 12 different teams. Here's what their contribution patterns look like. And you have to look really, really hard to see some pattern there. I mean, sure, there may be one or maybe two modules where one team seems to kind of dominate, but in general, this is collective chaos. So what this means is that you basically have 12 teams that work in the same parts of the code all the time on different things, since they work on different stories. Not only is this a communication disaster, it would also lead you to miss synergies between different features. That is an opportunity to make simplifications in the problem domain and solution domain. So please, align your architecture and your organization. Your code is going to thank you for it. And measuring how well your current architecture supports the way you work with it is a first step towards real improvement. So I hope you have enjoyed this journey through the field of evolving code. Ultimately, it's all about writing better software. Code that's able to evolve with the pressure of new features, novel usages, and changed circumstances. And I'm pretty sure that writing code of that quality will never, ever be easy. So we need all the support we can get. And I hope that this introduction to software evolution has inspired you to investigate the field in more depth. And to get you started, I put together a number of references here. If you want to dive deeper into this, I have a whole book about it, Your Code as a Crime Scene. I also blog about it at mpr.com, where I have a bunch of different case studies of real-world code bases. Now, before I leave a few minutes for questions, I would like to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thanks.
Hello. All right, thank you. So we have a few questions coming up here. We can just start maybe with the first one.
Yeah, so I think I answered that later in presentation. So the tool I use myself for the case studies is CodeScene. Since I'm one of the developers on it, I eat my own dog food. But you could also use the open source CodeMat tool that I pointed you to.
All right, so how did you generate the hotspots?
Yeah, so again, I use the tooling to do that. What happens in practice is that, first of all, you calculate the change frequencies from your Git log, which is pretty simple to do. It's really just math, right? Sum it up and prioritize them according to how often they are changed. And that's basically the most important data, because change frequencies have a really strong predictive power. I have a bunch of references to that in my book, to real research studies. The reason I add this complexity dimension, which is something you can just scan your code. There are tools like Clock, which basically is a Perl script that counts the lines of code. The reason I want us to introduce that complexity dimension too is because it helps us filter out some false positives. So for example, it's not as useful to learn that your top hotspot is a file with one line of code that's called version.txt, right? So complexity dimension helps us get rid of that. So, would you suggest dealing with technical debt while addressing user stories, or shall a team consider tech debt-focused iterations on a regular basis? Well, I think this question relates to what kind of debt we actually talk about. So the real kind of technical debt, the original sense of the word, is, in that case, technical debt is actually a strategic decision, right? You make a trade-off, you trade quality, future maintainability, for getting a feature out fast. And in that case, I think you actually need to plan improvements. It should also be a strategic decision when you do those improvements. However, I also think there's a lot of technical debt out there that's more of the reckless kind. It's simply because the code is bad. And again, I think you should measure all the time, because we have a lot of code that's not up to par, and we cannot possibly address it all at once. So that's the main reason why I think it's so vitally important to prioritize it. And I'm pretty sure that the team should have the mandate to be able to do that prioritization themselves on a smaller scale and address it as a natural part of their workflow.
So we have, I think, maybe you can answer that. Are your slides available online?
I'm going to tweet out the link to them after a presentation.
Cool. So before you go, I would like to give you a little gift from the craft kind of conference organizers. Thank you so much. Please, a round of applause for Adam.
Thanks.